About him before he proceeds to the lecture. So, Dr. Sarat Sreepathi is a computer scientist with 20 years of experience working on the world's fastest supercomputers. He did his PhD in computer science from North Carolina State University. He's worked as a research scientist in the Future Technologies Group from 2013 to 20 and the Computational Earth Sciences Group from 2021 to 2025 at Oak Ridge National Laboratory, the largest laboratory for open science in the United States. His research interests include high-performance computing, computational climate science, performance analytics, exascale code design, and many more. As a performance coordinator for the Energy Exascale Earth System Model (E3SM) project, he led an interdisciplinary team of scientists across national laboratories to focus on application readiness and computational performance on leadership class supercomputers. With this brief introduction, on behalf of IITM, I would like to invite Dr. Sharat to provide his talk on the title Climate Modeling in the Exascale Era.
Thanks for the introduction and thanks everyone for coming. Hope you can hear me clearly. So yeah, I wanted to kind of give a breadth of a talk. So I think if you see a topic that is of interest and I haven't included enough detail here, please feel free to follow up offline and we can have a discussion later on. So the idea is to cover kind of the diverse aspects of the project that have been involved with and go from there. So just a little bit of background. So I will use some terminology, some agencies which may or may not be familiar to people here. So the E3SM project is funded by the US Department of Energy. So think of it in terms of the equivalent would be Department of Atomic Energy here. So the history of this organization dates back to the Manhattan Project where the first nuclear device has been built. So Oak Ridge National Laboratory was one of the first sites for and the first operational site for a nuclear reactor. So that history has kind of transformed from the 70s into open research. So that's why I was interested in not the weapons part of it. So they are now one of the largest open science laboratory, and we are part of the national lab ecosystem there. So we do collaborate on a lot of projects across the national lab ecosystem. So the primary funding for the climate work comes from the Biological and Environmental Research Program there, the Department of Energy. It's a sizable budget, but our focus is more on the climate scales and to answer questions for energy policy requirements. So I have just included a couple of things that are kind of relevant to climate work here. So I'm involved in many computing communities and then some of the advisory boards, but the ones of relevance are basically we have an interagency council, which is across US federal agencies to try to figure out how computational advances can help weather and climate science. So I'm the DOE representative there. I was also involved with the WCRP program for kind of outreach with the European partners and others to discuss outreach techniques. And then this SIDAC, this acronym stands for a interdisciplinary research program within Department of Energy. The idea is this funding program which kind of does both computational science work as well as domain science work. So it's not just one, but it's a combined computer science community and the funding agencies and the domain science communities getting together. So I have been part of these efforts for 20 plus years, initially as a grad student, and finally I'm on the coordination committee there where we're trying to see across projects what are some common themes and how can we address more collaborations in computer science and domain sciences. So in short, the E3SM project started out in 2014. Essentially, this is a fork from the combined effort we had with the National Science Foundation in US. It forked out because the focus is kind of diverging at that point where Department of Energy wanted to kind of move towards a model development activity which is more in tune with exascale computing paradigms that are coming up. So this was a decadal strategic plan that we kind of put together around 2014-15 with the goal to kind of target Earth system modeling activities for exascale. So kind of at a high level overview, it's a global Earth system model. When we first started out, a lot of the components were shared with CESM that some of you are familiar with. So the one big change that we did initially was switching over to MPAS Ocean. Whereas CSM initially was using POP and then MOM. Further development, we actually have our own atmospheric model, which diverged very much from. So now, the latest generation, we actually have a C++ based new model, atmospheric model written from scratch. So that's the computational heart of the computer model. And then motion, we are also working on a new C++ based model to address challenges with computing. So we do have other components, land heights, sea heights, and then there is a human element, which we're trying to bring in economic factors and also human changes, and trying to see how to couple that with the integrated system. So as I said, the goal was to use exascale machines effectively and for good climate science applications. So everything that we have done in E3SM is open source and open development. So what that means is every new development is being out in the open. So anybody can go to GitHub, look at the project current state, and even track the new developments that are going on. So the way we differ from CESM is we are not really an organization set up for community support where we're helping grad students run things or something like that, but we do have collaborations with key partners. So functionally, we have, so this is the third phase of the project. So we have been running for 11 years now. So this organization tends to, leadership structure, we try to mix things up. But now this phase, we are at a stage where we have some of the component level model development that is going on this side. And then there are a couple of, coupled system integration that is more model tuning for coupled configurations. And there is a computational infrastructure piece to it. And then there are science groups which actually take the developed model and run the simulation campaigns and then try to address science questions. So that's loosely the structure. And then we have some cross group activities for computational performance as well as AI. So I am responsible for both these parts, so the performance aspects across the project as well as the performance infrastructure for so this is a fairly large effort. So 30 million a year and roughly 10 years plus. And then, so most of them are working full time on the project, and some senior folks will be like half and half, and some other projects of strategic importance. So it's been going on for some time. Not all of them are, it's a mix of expertise. So some of them are primarily domain scientists. So a subset is computational sciences, and then very small group computer scientists. So, but we try to be interdisciplinary in the whole thing. So in terms of timeline, roughly, I don't want to go into a lot of detail here, but the idea was when we started out, we were on CPU-based supercomputers. And when model development started, I got involved here where we're trying to make the switch to GPU architectures. So the initial model configurations that were done and submitted to IPCC and CMIP6, those were driven out of the CPU-based models. So version 1, version 2, and even version 3 is basically a CPU-based model for the science runs. But the capability development has been going on from around this point where we had a lot of focus on doing GPU model development. So initially we started out with atmosphere, and now we are doing the whole coupled thing on GPUs. So right now we are around here, and basically we have the atmospheric model that is ready and used for science. That is the new C++ based model. And we are now working on the ocean based C++ model. So previous configuration, we were able to get some regional refined mesh and other configurations for that. So at a high level overview, these are the 3 production configurations that I would say we had. At the standard or low resolution, you had 100 kilometers in atmosphere, 30 to 60. And this is a fairly inexpensive model for us to run and on CPUs. So that was used initially for all the deck runs, the 500-year kind of simulation campaigns. So the high resolution on the CPUs was quite expensive. And also we needed to have a big block of allocation. And the way the supercomputing allocations work in the Department of Energy were, we had to write a competitive prep. We don't just have our dedicated resources. We can buy a few machines that we own. So those we can control. Like we had 3 $5 million machines that we control. But these $600 million or $500 million machines, we don't really have exclusive control over them. So there is a competitive process for getting those. And that's where our GPU developments enable us to make a strong case to give us, those allocations. So these high resolution configurations we were running from V1 on CPUs. And now we are at a place where we can run the 3-kilometer global atmosphere. And now we are getting into the coupled territory where the computational part is not the hindering limit now, but just getting the ocean and ocean 3-kilometer configuration tuned for coupled runs. So when they started out, these were like 40-day runs. It was sub-seasonal. We are now able to do decadal runs with this. So and some regional refined configurations that we have. Yes. So beyond V3, where we are at, is the idea is to have a unified model which can support all these kind of production configurations. And just briefly, from a computational standpoint, this is where I see the high resolution, not the ultra high, but these are the relative computational costs. So the x-axis is roughly all the CPU cores and how much time might have been spent on each component. So for us, atmosphere and ocean followed by ice are the primary computational components. And
Sarat, this is what resolution?
Again?
This one, the computational cost is what resolution? 25 kilometer? It is CPU.
Yes. So 25 kilometers. Roughly. So as you go up, so the atmosphere becomes a lot more expensive. So at 3.25, this component kind of.
I believe you said that after that you went on the GPU. So your 3 kilometer and all, they are completely on GPU?
3 kilometer, the whole atmosphere is on. Yes. So,
atmosphere only?
Yes, atmosphere.
So then you are making hybrid GPU and CPU for ocean and all on the.
Yeah, because some of these are, in terms of code, they are quite big, but size of core lines.
Actually, I had some question on the code, but I think maybe I can ask. If you allow, I can interrupt and repeat.
Sure.
So actually, you wrote that everything. I told everything in the C++. Is it?
Not everything. So we are trying to target the biggest part first. So atmosphere is all in C++ now. So ocean is halfway, like the model is halfway done. So we have a hybrid model where we have both the Fortran components and C++ components living together right now. The V4 that we are targeting in the next year or two would be more C++ than Fortran.
Okay, so if it is hybrid C++, then what about the your like version of the MPI and version of the parallel FFT in Fortran and C++? Because both have
in our top line. So we handle the interfaces for different components and handle the flux transfer and everything between Fortran and C++ kind of seamlessly. So that infrastructure we have built.
Which MPI CH was there?
Let us
Okay, fine.
the questions because otherwise others
So
will
that's why I asked whether I can, because it is so many things are coming together.
should not lose the interest.
Okay, fine.
So I will go to quickly and then we can. So just at the highest level, the supercomputing landscape right now, we have a machine at Oak Ridge called Frontier. It is based on AMD GPUs. So each GPU here is kind of virtually 2 GPUs in one. So we have about 64K GPUs, AMD GPUs on one machine. And then there is another machine called Aurora at Oregon National Laboratory, another lab, and there are Intel GPUs in that architecture. So these are the 2 big machines. So this is a Exascale, both Exascale, this is 1.2 petaflop. This is deployed in production from 2022. So we had early access, so we were working on it from 21. And then this machine became in production kind of roughly this year, actually. So it was kind of delayed because of Intel roadmap issues. So yeah, in terms of programming model, getting a climate model ready on GPUs is a hard thing. It takes, I would say conservatively a decade to kind of get to that stage where you start putting in a lot of energy there. So we had to rewrite the whole atmospheric model from scratch to get the performance that we required out of these things. So we chose what's called Copos for doing this abstraction. So this is a kind of C++ library that allows us to target multiple GPUs. So we are not tied to one GPU. So it's not a NVIDIA specific programming model. We can run on all GPU architectures. So So one trade-off that I see globally with these programming models and climate. So there are others who have tried to do this with OpenACC directives. We have done it in the beginning of our effort. There are limited gains, and also when we were getting new architectures, basically we were running into maturity issues with compilers. We had very strong vendor collaborations with all the major, compiler and other vendors, but even then there is a lot of flux when you have new architecture. So they were lagging behind even when the machine is deployed. So we had to abandon some OpenACC directive approach when this was not becoming feasible for us. So the other thing that is very popular in Europe, European models, is basically trying to do their domain-specific approach. So Cyclone is the Met Office. They were trying to do this for Elfric and their next generation model. So they try to abstract away complexity of the computer architectures by putting a layer on top. But even these things have yet to prove themselves in terms of performance at the highest scales. The grid tools can perform, but uptake from domain scientists is difficult. So you don't want a code base only computer scientists can read. That defeats the purpose of a climate model where you need continuous development and domain scientists to be able to contribute and tune it. So we picked C++. Reluctantly. It was not the first choice where all the climate scientists were so eager to jump into C++. But that became the de facto pathway to getting on Exascale for us. So yeah, just the atmospheric model, roughly at the high level, we have dynamics and physics, and many people ask me about the DICOR. So basically, it's a spectral element-based method. Splits the horizontal and vertical spectral element and finite difference in vertical direction. And physics, we do integrate a lot of packages. I will give the details in the next slide. So we have various microphysics. So aerosols is still under active development. We have a C++ version in development. So radiation and macrophysics, we have already ported all the rest of to GPU.
So this GPU exercise you are doing out of theoretical curiosity, or it has some benefit in terms of those subroutine which you have?
Yeah, so we needed it to even run on the machine. So our supercomputers are all GPU based. So we cannot run a CPU based model. And the way the US supercomputers are set up, we call them capability versus capacity. So if somebody has a small job, so example, our guys wanted to do large ensembles. So with large ensembles, you can fill a large supercomputer. But DOE would not allow us to do it. There is no way they will let us run, a small mid-scale parallel job and fill the whole machine, because that's not the mandate from both the computer science perspective as well as the domain science perspective. For us, the idea is to kind of push the bleeding edge of both. So for us, we have to push both on resolution, and for that, Fortran model was not scaling up. So we had to do this out of compulsion rather than just theoretical curiosity. So just in terms of details, so the home DICOR is the one that we have used for dynamics. Microphysics, it's P3, which is our model. So you can look up the references, but the idea was basically some of these are ported to GPU already. So even if there is a potential for integration into other models, people can take a look and see. These are all open source. And radiation is one big component where we have multiple ports of this, and then the latest C++ version that we have is actually quite performant. So coming to our 3.25 kilometer configuration, I just wanted to kind of give you rough details of this. So we have about 7.2 billion degrees of freedom for this run. So this was the kind of a large scale benchmark run that we did for supercomputing conference. So in 23, there was a special award set up for the, it's called ACM Gordon Bell for climate science modeling. So they initially wanted to push climate modeling centers into Exascale and try to see how people will respond to it. So we were the first winners of that award. And basically this is the configuration we ran for that. So in terms of computational performance, all these architectures, we were able to run this. So I can go into the detail, but basically this one is that the 1 degree resolution, because you need performance on GPUs for the low end as well as the high end. Because when GPUs are given a lot of work, they will excel. You will get a lot of speed up. But if you are running a climate-centric configuration, you are not running at that higher resolution. So what happens is your GPUs benefit from the GPUs won't be that high. So you need a model which handles both cases with very low overhead. So here we actually have pretty good scaling and also pretty good CPU over GPU speed up. Beyond a certain extent, the problem is too small on that supercomputer. You need to go to a final resolution for that. So when we say scream, this is our atmospheric model run at a kilometer scale configuration. So this was the first time people had run on multiple GPU architectures, and we had a long-standing goal of 1 S5PD. If you're familiar with this throughput metric, basically the idea is if you use up the supercomputer for 1 day of computation, how many years of climate can you simulate? And for practical reasons, if you are able to get at least one, you can do decadal kind of studies with the kind of supercomputing resources you have. So we were finally able to cross this in 23 with our model, and this resulted in the 23 Gordon-Bell Prize. So this was a initially I was the initiator for this effort, being the performance lead for the project. We had some skepticism from, even within our leadership, where people wanted to do domain science and not just target a supercomputing achievement. But this turned out to be a very big deal for us, both in terms of visibility and funding and everything. So this kind of opened doors for us at many US level federal agencies and other places where they were looking forward to kind of incorporating this capability. So sometimes even if domain sciences are a little reluctant, there are advantages of pushing the frontier on the computational side for building capabilities. This, I'm just giving you an architecture diagram for the supercomputer that we ran on. The one point I want to make is climate models are very sensitive to memory bandwidth. It's not just about buying the latest GPU, because you are not it's not AI workload. You are not just pushing flops. You are trying to get the most throughput out of the model. So in terms of memory bandwidth, all these hybrid supercomputers with GPUs, what's happening is all your memory bandwidth is also on your GPUs. So even if you have a hybrid machine with still CPU cores and GPUs, your CPUs are so puny. Like for us, in terms of flops, it's less than 2%, and memory bandwidth less than 2%. So if you are not targeting GPUs, you can't even use the machine. We're just wasting the resource there. And this is the scaling run that we went for the award submission. So on the left, I have the full model configuration where we have active atmosphere and ice and prescribed ocean. And on the side, I just have the atmospheric model throughput. So even here, the full machine is about 8,000 nodes. And we are able to scale all the way, but the scaling efficiency goes down at the highest level, because even for this kind of configuration, there isn't enough work for all the GPUs at this point. So they are still the communication costs are more than the computation cost at that point. So this is, we crossed what we were able to do 458 days of climate model for 1 day of computation. So initially we were under this when we first started this work and submitted our paper. By the time we did the final camera ready version, so to speak, I was able to get about 54% improvement. Because at scale, there is a lot of complex tuning, MPI, both device to GPU communication. So there was a lot of mix where, even though after all our development, after you get on the machine and run at scale, you're still finding inefficiencies, and you needed to address that. So we were still able to improve this that much in few months. So this was in summer of 23. So this is just one snapshot I wanted to kind of highlight. It still does useful things. So this is a radiative flux measurement from a satellite, as well as the simulation outputs from screen. So Since then, we have, additional papers on the atmospheric model where we go into a lot more detail about the capabilities and especially at the decadal scales, what new science we are able to do. But just a kind of snapshot of that. I want to switch gears into another model formulation we have developed in the intermediate level where between 2015 to 2025, in the middle, we were at a place where we didn't know whether we will be able to do kilometer scale models globally. So what we wanted to do was a super parameterization approach where we had, more like the 100 kilometer or 25 kilometer global resolution, but able to get effective resolution of kilometers by using a cloud model, cloud resolving model. So we have integrated. So we started with a library called SAM and incorporated it as a subgrid model. So this is basically within the atmospheric model time step, we are calling a cloud resolving model and integrating it back in. So we developed various versions of it, first using OpenACC directives, OpenMP offload, and then finally C++. And we further down, we actually built a new die-core version for CRM, so we have been experimenting on that aspect as well. But then our global CRM, global cloud resolving configuration was ready enough that we don't need this anymore. This was our stopgap measure where we were trying to do that. So during this time, we tried the MPAS Ocean port as well with directives. We got very limited speedups from this. The MPAS framework as it is written is not very amenable for GPU porting. So NSF and NCAR are finding it out. It's a very uphill task. And even if you throw a bunch of 100 NVIDIA engineers at it, you will get some speed up, but it won't be portable. And it is an uphill challenge for them. So, and this is the reason why I'll show you why we are building a new version model. So in terms of performance, again, this is a large scale, like strong scaling plot. So this was the earliest supercomputer from Frontier. This is a 200 petaflop machine that we had. And we were able to scale up to the machine, but as you go up, your efficiency start losing because, again, even a big, very strong, like heavy configuration, does it have enough work for the full supercomputer? So, yeah, one topic, yeah. So quickly, the ocean model. There are a bunch of science drivers where we wanted to target, high resolutions and, complexity in the coastal shell, coastal areas, trying to incorporate all that. And there were so many efforts with the MPAS Ocean. First one was, Navy funded, didn't go anywhere. We had a program through SIDAC. So many efforts. And then finally we decided, by the time we finished the atmospheric model development, we decided that we had to start from scratch and develop a C++ based model. So this time what we did was that we wanted to make it easy for the ocean developers themselves to write the model. So for the atmospheric model, we had a bit more hand holding. So because that was a prototype phase where we were doing that. And now this time we wrote on top of the Popos library infrastructure, we wrote some helper functions for them, so to speak. So this made it easy enough that, all the domain scientists could pick up and write the, the solvers, the infrastructure, the actual computational kernels themselves. So at the core, what you want from your GPU-based models is basically the infrastructure is ability to launch computation on GPUs. That's the major thing. And data transfers, you want to minimize as much between CPU and GPU. Because if you're still transferring data back and forth, you are not going to see performance improvement. So the way the code looks like, for Fortran developers, it is still a leap, but it's not a big disruptive leap. So a loop that looks like this on the CPU side now looks like this on the GPU side. So you just have some annotation which will take this computation. So basically, this is the same loop as this, and then launches it on the GPU. Things get complicated, and that's where, if there is complex kernels where you need performance tuning, we have ability to do kernel fusion, look at hardware architect performance metrics, and then look for optimization. But the core basic idea is, even with this kind of simple annotations, you can get a model GPU ready. It will still be effort, but it will give you, a support on multiple GPU architectures. So again, these are optimization strategies. I won't go into them. So some other infrastructure that we developed for this is, scalable Halo exchanges for the models and solvers, global reductions. And this was so we have a requirement, but that, things are bitwise reproducible. So when we make changes to the model, we want to make sure that, they are not, underlying causing any issues with changes where they're not supposed to be. So we do enforce this on every new development. So every new pull request that we get for the model, we have an extensive list of tests that goes into this. So even the communication supports it. So if you run something at multiple scales, it will still give you a reproducible result. So there's a lot of other infrastructure, but the idea is, how do we enable this development workflow, and how do we efficiently enable domain scientists with this? And this plot is about GPU to GPU communication, how we are able to optimize for different configurations. So whenever you have GPU-based machines, you need this kind of MPI-aware optimizations to take full advantage of the hardware. In terms of this ocean model is still a work in progress, but even already we're able to see like 1.4x on the CPU side. Just by rewriting the Fortran into C++, we're able to get 40% improvement. On the GPU side, we had phenomenal improvement. So 5x on one machine, and then other supercomputers. So on multiple GPU architectures, we are able to get 4x and 5x improvements, and that's the capability that we were looking for. Again, scaling plots with larger configurations, we scale pretty well. And so taking on time, I have a few topics, but I don't want to bore to death. I just wanted to kind of give a flavor of some things. And this is some performance infrastructure that I developed for our climate efforts. So the intention is we will develop some continuous performance monitoring as well as provenance tracking. So every E3SM model experiment that we run on a DOE supercomputer, we automatically capture the performance characteristics and the provenance characteristics, and we upload it to a central database. This lets us look at, summary performance graphs, look at load balancing issues. So we have so in that sense, even though we are not an operational center, we do keep track of, nightly tests, nightly performance regressions and things like that. So again, we had a bunch of supercomputing centers that we run. So everything gets centralized into a database, and people can just log in and look at their experiments whenever they want. There's a whole lot of backend that needs to support this. And one final thing, being at a Department of Energy lab, we had to worry about cybersecurity. So there are enough attempts to hack our puny climate information system, where I had to work with penetration testing people to get this thing bulletproof. So these things in terms of functionality, by the time you get there, you will have to address all these uncertainties. So this had a lot of features, like people run their simulations, they go on, they search for their runs, they can look into all the provenance, the model costs, a lot of timing level data down to the lowest subroutine level, and also looking at IO performance. Sometimes you have a machine degradation issue where IO will suddenly be longer. So instead of somebody taking a look and again running it or whatever, we have continuous data collection where we can address this. They come in, they say, oh, my runs are slower. People can take a look at it and then help out. And we're at a point where they don't even need to bother the performance expert. They can just look at it themselves and then, oh, this doesn't look right. So they will rerun or inform the sysadmin. So a lot of IO details, and also memory. So if somebody is doing a new development and they have a memory leak, these things will catch them, and then we don't have to bug them anymore. So this kind of infrastructure, it's both operational as well as enables research for us. If there is load imbalance issues, it allows us to kind of keep track of what can be done within the component as well as in the coupled configuration. So here, these are various sub-processes within the atmospheric model, radiation, microphysics. So we can track the evolution of this percentage just over time and over model version. We can address, does it look reasonable? What is the complexity we added, and is that the expected outcome? And also initially there was a lot of MPI optimization that we were doing based on these process layouts.
So this is a separate tool for profiling.
We built our own tools. So this is
It's a separate, it's not the part of the model, it's a separate tool. You have to.
so it is, so the model itself has hooks to our tool. So it is run along with the model. It will get all the timing information dumps.
It's the part.
But we will also have other supporting infrastructure that takes this, makes a lot of visual plot and some other analysis to even recommend whether something in there. So with this, I mean, I think I have a few topics, but I don't want to get into too much, but so I will skip a few slides. This idea was whenever you have a new architecture, how would you address it? How would you evaluate it for your climate workloads? That might be of relevant as you're looking at new architectures for your workloads. So we got access to the Japanese supercomputer Fugaku a few years ago, and we were trying to address, compared to the GPU machines, is it good enough? And especially for climate, if we can avoid, GPU machines, that's a good thing. So we had designed some metrics and a lot of workloads. The weird thing was, in terms of absolute performance, so a lot of these were down below multiple generations of Intel and AMD CPU architectures. The top bars are basically GPUs. The higher is better in this plot. And A64FX, contrary to expectations, really feels like a subpar CPU. So the biggest advantage it had is in terms of power efficiency. And even with that, it is still not beating the GPU. So at that time, this was a strategic question at the US higher level where what is the, so Japan made a play for CPU-based supercomputers. We made a play for GPU-based supercomputers. Is there, benefit in the other strategy? So at least for our workloads, and I know I have worked with a nuclear fusion workload for the same architecture, we didn't see a benefit. In fact, there is, their performance improvements were not really, you are better off with the CPU machine. So there is a lot of lagging support from vendors and whatnot. So that's the takeaway. We did a lot of architectural analysis to figure out why. But again, this is useful for Fujitsu, not nobody else. But this is the level of detail when we go into, trying to debug something. So there are, instruction stalls on some loading data and whatnot. So one thought I wanted to kind of, as you look at, for us, we were looking at Exascale and even beyond, how do we prepare for these things? And what can we do as application groups or centers? So there is this idea of co-design. It's been kind of, fashionable in the computer science community for a long time, but how effective is it and what can we do to make it more effective? So I have driven, vendor relationships between E3SM and Cranes, IBMs and, NVIDIAs of the world. There are some vendors who are very responsive and you have long, deeper engagement. And then there are others who are more, transactional. It's not just the next procurement for us. We want to build a long-term relation where, we are influencing their strategy, they are influencing ours. But hardware influence is kind of a difficult thing, especially when AI or some other market is driving their dynamics. So when I look at, the upcoming architectural diversity, so things are evolving at a very good pace on computer architectures. You will see so many different varieties of things. Even in India, like RISC-V, new things will come up, but you need to evaluate whether that they fit your workload. And what you also need to communicate what your workload requirements are. So there is a distinct community. It's like climate sciences or other science communities, and then there is a computer architecture community. Until you connect them and talk in a common language, they will be disjointed. So you will just get a chip which you have to use. You don't really have a say. So the idea is to make some good representative benchmarks and workload characteristics that you can communicate down to the vendors. And then I just put in there is a lot of, at least for us also, and here, there's a lot of noise about quantum computing. I've been asked to give talks on, how we will use it in the short term. And the short answer is there is no short-term application that I see. And even long-term, there is just a lot of uncertainty. We will probably do nuclear fusion before usable quantum for 20. But it's evolving. So whenever you're looking at emerging architecture, you just need to keep track of what's going on. So yeah, I will leave this thought. So when people think of computer architectures and new things, they kind of worry about the disruption to their science workflow. So I think this should be looked at as an opportunity, and how can we kind of leverage the new architectures and for new capabilities. It's not just a stunt, because you will run out of stunts soon. So the idea is to enable new science capabilities, and how do we kind of communicate and collaborate on that. And especially at the high-end scientific computing, you need to have good vendor relationships that go beyond sales and marketing. You need to communicate key kernels and workload characteristics to them. So even the small design trade-offs, like AMD GPUs, they picked a different cache size from the NVIDIA GPUs. And that hurt a lot of applications. So you had to kind of, by the time they bake in the chip, it's too late. Sometimes if you give them a part of a benchmark where they can integrate into their workflow, they already know the trace of your application. They will know, oh, a lot of applications will probably be hit by this small change, which we think might be good for AI. Now it's going to kill our HPC. So there are things where it's still a useful exercise. You may not be able to influence NVIDIA's next chip, but you are going to influence the next small design decision within NVIDIA's new chip. And finally, this is more like, future wish list. Let's say we're spending so much money, and even India, they will spend a lot of money on NSM 2.0 and whatnot. So the idea is, when you're looking at this economics, I mean, Fugaku was $1 billion in including R&D. And you got to wonder, like, what are your national interest applications? Like, we are not building this machine just for fun or just to make a statement. So what is the critical national interest that is served? And if needed, if there is, custom hardware that we can make in an economical way, that those dynamics are changing now. Like in 5 years or 10 years, a custom chip for your application might actually be a reality. So just to keep an open mind about those things. So I will, one final visualization I wanted to show, pretty picture at the end. So this is some parallel clustering work that we did to look at satellite imagery and look at, evolution of regions. So we had parallel algorithms for this. This is not E3SM, just something that we did. So I just thought I would leave it there, and then we can take some discussion. So.
Thank you, Sharat. Thank you for showing us so many new things, and also a brief overview of CPU versus GPU, which is a haunting question, and also a beautiful comparison of Frontiers versus Fugaku, which I had its curiosity from so long before Fugaku. So that's a good thing. And with this note, I'll open the floor for discussion and can have some healthy discussion about it. I don't think Vipin needs a mic.
I have two questions, but I will just go for one particular thing interesting for everybody. Is communication versus the computation, you said.
Yeah.
And second thing, you said that when you were developing C++, it was faster than Fortran.
Mhm.
Is it just because of the changing the language? Because generally what the concept, you said we had that Fortran is the faster than the C++.
So yeah. So it's a valid question, because if just switching a language won't give you much, like unless you're coming from Python to a better, native language. But so Fortran, in the ideal world, I have been involved with the new Fortran standardization efforts also. In the ideal world, all the Fortran features that we have, if they're implemented well by the compiler vendors, you don't need to move, because think of it as the domain science specific language for scientific computing. Because Fortran has everything that you need for scientific computing, but the reality of the world is, if you look at AMD, if you look at Intel, they have so during the same decade that we were doing all this development, they were trying to develop new compiler versions, and they moved from their old backends into LLVM, which is a open source new compiler backend. That was a lot of disruption. They didn't even promise us basic functionality like MP, like just OpenMP offload to GPUs. Intel couldn't get it ready until 22 or 23. So even now, if you just want MPI directives with Fortran, it won't work on GPU. So GPUs are the reason why we had.
Yeah, that was my question. It is because of the C++ or because of the GPU on the C++ on the GPU?
No. Oh, so even on CPU, we saw benefit because we are doing aggressive optimization. So Fortran does it, but there are still gaps where the compiler won't be able to do
But
everything.
then what about the accuracy? Like
It is-
we are going up to the double precision.
We were bit for bit with our Fortran version.
Okay.
So we made sure that we are bit for bit when we did the validation, when we did the.
And did you get any benefit in communication? Because I think this is the spectrum based code, no? It is all.
Spectral, yeah.
So spectral. So what is happening for this all-to-all communication? Any benefits from Fortran to C++?
No, that's at the MPI layer, and we had a lot of. So I. If I.
Anyway, we have to do all-to-all communication.
Yes, and there are ways to do it, and then there are strategies at a very. Oh, my machine. So,
that might be the novelty.
and that's not for this comparison. So the DICO, like the atmospheric porting work, that optimization came from compute optimization. It's not communication. So if I have some slides.
So of your slide, you have shown that the Fortran and C++ is not much different performance wise.
Yeah, it is. Yeah, there is a slight improvement. It's not dramatic as GPU. The idea was GPU, but the point was to make that by going to this common code base for CPU to GPU, we didn't sacrifice our performance on. So because whenever people do this, they lose their performance on CPU. So the idea was we didn't lose our performance on CPU.
That is the point.
That's the point. Yes.
Gained any performance as such much.
Yeah.
Okay, I will leave for others.
So when you try to change from Fortran to C++, how much effort and what is the plan you had for C? There are several modules.
Yeah.
And as you mentioned rightly that there are some RTMs and they're just better.
Yeah.
So what made you to decide which one will go first? And
So
how
I
do
will tell you,
I completely?
Yeah. So initially, we tried to do this with OpenNCC directors. And we had a small team within the performance group that tried to do this for the aerosols within atmosphere. They spent a year or more without much progress. So meanwhile, we had another team trying to do this on ocean. So I was familiar with both these directive approaches, and I was contributing more to the ocean side at that time. And we realized that the frameworks are coming in the way, especially the data dependencies the way they are, at least in our code and most codes out there. Because I have seen this in NOVA models as well. Even weather models, climate models, wave models. There is a lot of implications and intrinsic decisions that people made when writing CPU-based models. The trouble with GPUs are the moment you do data communication, you won't get much speed up. So we had to port the entire thing to GPUs. So for us, then we decided to do a kind of a port of a small targeted effort where we started with the DICORE. So atmospheric DICORE was the first one where we said, okay, we will take home. And home is what was the DICORE. So we said, we will build a C++ version. So that was a small team. Actually, it was a side project for 5 years. So that took that long for them to prove that we have all the, all this validation that went into it. And this was in the era where GPUs were not the, it was not the definite answer that GPU was the only architecture. Because we were targeting KNL, Knight's Mill, all the Intel architectures, which were completely different. So we were trying to get vectorization performance on Intel hardware and also GPU performance. So there was the common code base couldn't handle these kind of optimizations well. But we were still, so the C++ helped us where we can target both, but also maintain a common enough code base for that. So it is a long effort.
So one more thing that to his question, you have answered that you have tried to maintain the bit to bit.
Yeah.
It is hard to believe for me at least.
Yeah, so I have, so the reason is bit to bit in the sense like when we did the validation. So it's not like, every V0 to now we maintain it. That's not the idea. The idea was when we did the port of atmospheric model, the idea was to make sure that whatever science configuration we are running with the Fortran version of the model, we are able to bit for bit reproduce it with the replaced model then. So after that, we have a number of new developments which will change the answer. And those we validate based on our, we have a extensive V and V suite where even climate changing and changing answers are integrated over the years. So we will do all that. But I was just speaking to his point about how the porting was done and whether we had accuracy, same accuracy.
It is the case that we could have tested only on the CPUs only.
The numerics change on the GPU side. So if your order of computation changes,
That's
yeah, and now you have to make sure that your GPU version is correct.
Yeah.
So
anyway, there's so many questions. I'm going to discuss. Yeah.
So suppose instead of developing the entire code in C++, I was to basically train emulators. How is the speed up compared to emulators versus a C++ code running on GPUs?
So emulator, right? So even we have started working on emulators because AI is the hype du jour. So everybody needs an AI option. So emulators are they are a bit expensive to train, but once you train it, the inference cost is negligible. I mean, you're talking about having a few GPUs to, but how much trust would you have is a different story. Whether they are a good enough replacement, but the overall idea is the computational cost of inference is very small. The training part, for that, what we have to do is, you need very high resolution and high temporal frequency output to train it. And those runs will be, again, at an exascale level if you're doing it at a kilometer scale model. So the training data set itself will be the costly one.
So maybe the parameterization can be emulators and your dynamical core can be C++, right?
Yes. Yeah.
And
that might be
bottleneck will still be the data transfer between the two. Like if your ocean model is running on CPUs, and this one is running on GPUs, the bandwidth is still the
So that is fairly at a very in terms of you're not doing it at a sub time step at every loop level, right? You're doing it at a once a time step. So that is okay. The point is not to zero out the communication. The point is to minimize communication, especially in the compute intensive loops. So atmosphere and ocean coupling, they can transit across. I mean, in some of our layouts, they are on completely different nodes. So that can happen and we are still okay with it.
Nice talk, Sarat. I have two questions. You said Scream V1 is with Fortran, right?
V0 is with Fortran, but V1 is C++.
And you have implemented these CRMs, right? Cloud resolving models.
Yeah.
In which function you are trying V2 or?
Oh, so those are the backup option. If we didn't get Scream to run it, because Scream was going to be a long-term effort. So we had supplemental funding from Exascale computing project, which is a computer science research effort. So that was the NSM of US.
Okay.
There was $2 billion worth of funding, and they had additional money for us to look at other model formulations in addition to what we were doing in E3SM.
But this one also you have converted to C++?
Yes, so the cloud model, we have converted to C++, yes. Initially, we had OpenACC and OpenMP ports, and they were okay. But the reason we had to go for C++ was, AMD GPUs. HIP support for AMD GPUs, there is no OpenACC. So, if you want to run on AMD GPUs, there is a old version of Cray compilers which will support something, but you won't get good performance out of it. So you need something to do.
The CRM size you kept 4 kilometers or changed something?
No, these are effective resolution would be 1.7 kilometers, depending on the configuration. So the horizontal grid was about 25 kilometers, but CRMs themselves, we had a 2D CRM and then a 3D CRM.
Yes.
So those are, I think, grid cells like 64 by 64. So they are effectively grids. So we tried a few variations with those, but but now our focus has moved on to this global model now. So we are not running those in science configurations.
Thank you for the nice presentation, and impressive work. Actually, we also have the same issue. Like for us also, atmosphere is about like it takes a long time for the computation. And I think like for the E3SM six simulations we were done with the Fortran code. So for the CMIP 7, you'll be moving with the atmosphere in C++, and Ocean again will be in the Fortran.
CMIP 7, I think by the time we make a submission, maybe we might even move to Ocean on C++. So right now CMIP 6, the fast track CMIP 6 plus, we are doing with current Ocean. But come next year or end of next year, we might even have the Ocean part ready. So,
and as per you were suggesting, like before you also to make the whole thing atmospheric model into a C++, you take considerable amount of time.
Yeah.
So do you suggest like for us, it is radiation that is taking the most time.
Yeah.
So do you think like doing it by part, like if we first focus on only for the radiation, put it, if you want to put it.
Yeah. So there might be limited gains, and especially if you can do, like we had an idea where we had physics and dynamics decoupled, and we can, if you have a accelerator on the node where you have a GPU lying around, you can use it for the radiation while the model is still continuing to do other bits where you overlap both sides. Then you might see actually a good speed up. But if it is stalled waiting on it, then it kind of depends on the configurations and the data transfer costs.
You check like those configurations.
Yeah. So for us, like we had to go the whole way, but there is, so there is speed up always, like even with Ocean, we were getting 30% speed up or 40% speed up. But the reason for going to GPU, when you compare to a one CPU socket or two CPU socket, it needs to be, so for Summit, one of our supercomputer, the metric was you had to get 6x speed up with your GPUs compared to your CPU. And on Frontier, I would say, again, depends on your supercomputer architecture. So if you have so much computing power on your GPUs, and your CPUs are puny, then you have to have, close to 6x or 10x improvement over just using your CPU nodes. So that trade-off changes. And the reason that requirement is there, it's not just from us. That's a very, it's an effective use of hardware metric. And that is required for us to prove to DOE that we can use their supercomputer well. And we had to do that to show we can use 4,000 nodes of their 25% of their machine. If we use it, we have to use it effectively, and we need to run everything beyond that. We can't run, 100 10 node jobs or 100 node jobs. The idea was you need at least 2,000 node jobs that need to run on the machine.
Any other questions?
I have a small question in terms of costing. So suppose you are running a CMIP 7 model and you are going to C++. In terms of computational cost, mean time and energy in your how much you are saving?
As in computer energy or human energy?
Computer, both means manpower also.
Yeah.
How much you are losing, gaining, or efficiently?
So energy efficiency, we improved by many orders of magnitude. But the idea was by doing this, we are doing it in an energy efficient manner. So if we had to do Exascale with just CPU architectures, we would be running at, at least 100 megawatts. So our center, with the Exascale machine, it uses 29 megawatts at the peak. And we are able to stay within that envelope only because of GPU architectures. And that was the primary reason for, GPUs taking over the supercomputing world. Essentially, the energy efficiency for CPUs was so bad that there's Moore's law, Dennett scaling, and all these other limitations on the electronics side where we can't get energy efficiency with CPU architectures anymore. So,
Cost
is a good question. And cost, there is, so if I have that performance plot I have, right, with Fugaku, where both performance and normalizing by both power consumption. So this is the energy efficiency equation there. And then in a similar way, you have to look at performance per dollar. But right now, the GPU prices are so overinflated, you have to really figure out, like NVIDIA GPUs are inflated. If you take AMD GPUs, you might get better bang for the buck. And we did that. So for our Exascale machine, it's based on AMD GPUs. So both US Exascale machines are based on, AMD and Intel GPUs. There is a reason we didn't pick NVIDIA GPUs. They were expensive even when they were back then. And for us, I mean, we were getting, similar enough speed ups and throughputs on our applications with the other GPU architects. So that's the reason why you should never tie yourself to one vendor. So if you are dependent on one vendor and what their programming model, you are a captive audience. Like people say Oracle has hostages, right? I mean, that company. So in a similar way, if you develop and climate models live long after a computer architecture fad is done. So you need to be careful that you are building out for decades. So something needs to be portable across years and decades. So yeah.
Very simple question. So if we want to improve the performance, we have to divide the job between CPUs and GPUs. Yes. So is there any kind of application you have developed or something to scale up that?
Yeah.
If
So
GPU is intensely utilized, then how to?
Yeah. So the idea is, I mean, so some of the performance infrastructure we had, right? So it gives us the hotspots that we show you one. So if I take this, this is atmospheric model, and these are the dynamics runs. So we know that if some of these are communication intensive and some of these are computation intensive. So we have extracted some kernels out of our Fortran code. So we have a tool for identifying. So based on our timers, this timing infrastructure, we have identified some regions. Then we had another tool which will go out and pluck it out of a real run. So we are running your real production configuration, and we will have this tool automatically capture all the inputs coming into that particular sub portion and the outputs coming from it, and make a dedicated benchmark out of it. So you don't need to run the whole thing to represent this workload. Then we take it out. We try to see, is there enough computation? So we can even hand it off to our performance teams or algorithmic experts. So we have teams. So the atmospheric people can identify this. We can extract it. We can work on it to tune it or to port it to GPU, and then we can see the speed. We have done this kind of prototyping work before going all into C++. So that was done. Like we had incrementally ported Fortran, where we had many portions ported already to GPU. So there is a benefit out of it. You just need to see on your architecture whether that is good enough for your. So any improvement in your total solution time, right? That's what matters. So for scientists, the capability is if something takes 1 hour and you get it in 15 minutes, that's still a win. So as long as that is feasible, yeah. So some tooling is there where identification is one key thing first, and then extracting that out, and then you can independently develop the C++ version or a new Fortran version or whatever, compare it and validate it, and then you can drop it as a replacement. So we have done that before, but now we have, as we move to wholesale, then we can do all those lessons and incorporate them into the new design.
Was GPU memory ever
Yeah. So over the years, right? So this was so the first GPU machine that we had was Titan, which had Kepler GPUs. And so getting into the detail, but the CPU to GPU communication was over PCI back then. It is not a viable thing for climate codes. So we had ported things, but the only the application I was involved in which performed really well on those GPUs was nuclear fusion. So we had hotspot kernels where they are looking at plasma instabilities, so they can do ionic collision. So there is a very concentrated part of compute which you can take on the GPU and churn it for a while and then transfer back the data. So that was the only one where we had good improvements with Kepler GPUs, and that had to be done all the way down in code of Fortran and some intrinsic. So that was a very big involved effort. So over time, when we moved from that generation machine, this is about 2009 to 12, 13, that was machine was operational. Then we had this Summit machine, which is the those Volta GPUs. We had a better interconnect. So IBM has developed this CAPI interconnect where the power processors and GPUs can talk to each other. But even then, the promise of that unified memory where you don't have to worry about it and we will take care of the data transfer magically, that didn't happen. That was a disaster, frankly. So IBM also, every vendor overpromises. even after the machine gets into production, some of those capabilities never mature. So for Volta, at least what we did was, since we went all the way to get GPU resident code, we were able to see speedups on site. But others who were relying on data transfer, they were not able to. So IFS, that was one of the reasons. So Summit, they did the spectrum transfer and that's it. So as far as I know back then. So that was one of the reasons we cannot go on, 1 year you might get an allocation, but next year you won't get it. There is a scientific peer review both by domain scientists and then also by computational scientists. So they will evaluate whether your code is using the hardware effectively. So if they don't, they won't give you your million hours on a supercomputer. So those are the constraints that come into play. So if IATM, you might have your dedicated center, so you don't have to worry about it. But in general, that's the idea. Like the constraints are there externally to force things. So,
Any other questions?
but
Kilometer scale global model, what are the plans for validating such high resolution model globally?
yeah, so there is still work in progress. So the idea was to, so at kilometer scale, what are the process? So as we move up to that resolution, there are things that we have already identified as gaps. So some of the cloud parameterizations need to be tuned further. So just in atmosphere itself. So coupled model tuning for us, once we get a component ready, it will still take at least 2 to 3 years to get a coupled model ready. So we are at the early stages where we are kind of evaluating what the current responses are with our current coupling and then trying to adjust and address the gaps that we have. So right now it's at that phase. So the coupled kilometer scale, I wouldn't say it is scientifically, ready for everything. It is a work in progress at this point.
Anyone else? If not, let's thank Dr. Sarat again for this talk. Thank you everyone for joining, and I guess tea is around.
Oh, sorry for keeping you away from tea, but yeah.